Alright, so we are starting vectors today. It is the first thing we're going to be covering in Pure. Okay, all the statistics is now... Guys, all the statistics is now covered. If you want to turn to a page as reference, I am currently going to be talking about page 210? Yeah, 210. Okay. Well, not quite 210, but like pages following on from that page. Right. So, guys. Yeah, I've got one here that you can use. Right. Right. Guys. Right. So, for vectors, I'm not going to refer too much to the book because I think the book has a few issues with like how they've decided to try and go over some of the stuff. I think, it's not the most obvious thing. But previously used to do vectors in year 12 and in year 13 with a lot of harder vector stuff in year 13. They removed that last year so that you no longer do vectors in year 12. You only do it in year 13, which means that in year 13 you miss out on some of the harder vector stuff, which is good. Okay, it means the vectors aren't as hard as they used to be, and it's mainly a mixture of what used to be AS vectors with like one extra component to it. So it's not massively complicated, thankfully. Okay, but you guys won't have looked at vectors since year 11 when you did your basic 2D vectors. Okay, so you may remember, stuff to do that look like this. Oh, there's a couple of lines. Oh, the vector here is A and the vector here is B. How do I go there? Oh, A plus B. You remember that stuff? Yeah, that's basic and way too low level. Okay. Did you have to write vectors in a vector form? Like, did you have stuff like that? Oh yeah, cool. All right, so guys, the only difference now is there's going to be three numbers. Okay, because we're doing three-dimensional vectors. X, Y, Z are the Cartesian coordinates of points in terms of vectors, but we don't use X, Y, and Z for certain things, and we'll go over that later. But if you look on page, I think 212, they give you a little pretty picture of points. When dealing with three-dimensional vectors, it's quite hard to visualize these things because all our visuals are two-dimensional. We don't actually have really a three-dimensional way of visualizing this unless we start to learn VR and stuff and get your heads in like a three-dimensional space to find points. Okay, or I turn this room into a three-dimensional point and we can work it out from that. But there's different orientations of what graphs can look like. Normally there's the X, Y in the normal plane, the normal way that you'd expect it, horizontal, vertical, and then Z is like a depth. Okay, so you quite often see that. Although they've shown rotations of all these three things. What you need to know is a point is written as X, Y, Z. So instead of just X, Y, like your normal two-dimensional Cartesian plane coordinates, whatever it is, which is just X, Y, we've now thrown a Z on there, okay, to represent the third dimension. Okay, in terms of how your vector is written, your vector is written as X, Y, Z. There, easy, right? Okay, so the top value represents the X direction, the second value is the Y direction, the third value is the Z direction. Okay, so we need to be able to work out how to find a vector between 2 points. Okay, that's one of the things we're going to do today, as well as a unit vector, what we call a unit vector, which is part of also finding a magnitude. So a magnitude of a vector as well. They're the three things I think we're going to be kind of focusing on. Okay, so if I have a point such as A, which is 2, 3, minus 1, and I have a point B, which is 6, minus 5, 2, how could I get the vector AB? Find the difference. Okay. What was that? B minus A. Okay, that's it. So if you want the vector A to B, the formula for that is B minus A. Okay, the second letter, take away the first letter. Okay, so in terms of our vector, that would look like 6 minus 2, 3, minus 5, minus 1, minus 2. Okay? Obviously, be careful with your double negatives. If you're taking away a negative, it's an add. We should know that at this point. However, people still make these mistakes to this day. So 6 minus 2 is 4. 3 minus 5 is 8. I chucked a minus in front of a 1. Sorry. Hang on. What's wrong?
Minus 5 minus 3.
Oh, thank you. Minus 5, minus 3, and that should be 2 minus 1. Sorry. I swapped them round. Thank you for noticing. Cool. So 6 minus 2 is 4. Minus 5 minus 3 is minus 8. And 2 minus 1 is 3. So obviously, you can make mistakes like I just did, where you just accidentally be a bit careless and get your numbers the wrong way round. So it's really important that you take a bit more care than I do. I'm always going to be a bit sloppier because I'm not trying to pass a test, am I? Okay, so that's our vector A to B. Easy, right? Cool. So, what happens if I said, what is OA? Well, O is 0, 0, 0. So what would vector OA be? Sorry?
It's just A.
It's just A. It's just the values of A, yeah. Okay? So, O is the centre, yeah. So, origin, okay? So if you've got a point, 2, 3, minus 1, if I want to go from the origin to that point, it's the exact same values, 2, 3, and minus 1. So, OB would also be, I know I've kind of swapped between lowercase and capital. That's not great. I should have called, to be fair, I should have probably called these capital letters because we tend to use capitals when dealing with vectors for some reason. So that is not what I wanted to press. That should mean AB, that would be B minus A. Okay, so OB is 6 minus 5, 2. Okay, so another way of writing AB would be to say OB minus OA. Okay, that's the better way of saying how to get from a point to another point is the origin to A minus the origin to B. Okay, there's other things to do with those, though, that you'd have learnt when you did these ones. You may have had like 3 lines. Try to think of what one of those would look like. Oh yeah, you might want to do that. Okay, so if this was A, B, and C, you would say that A to B is A, B to C is B, but A to C is A plus B. Okay, so that's kind of the rules with vectors that you would have learnt back in year 11, is that if you want to go from one point to another, you can work that out by the vectors, the other vectors around it. Okay, you don't know A to C, but you know A to B is A, you know B to C is B, so put them together. There's an additive nature to vectors. Okay, so let's give an example of that. If I know that PQ is 2 minus 3, 1, and I know QR is 4, 5, 6, what is PR? What would I do? Do you add them?
Yes.
Yeah, you would just add them. Yeah. Okay. Right.
I told you.
At least I'm pretty sure you add them. I just sat there for a second going, do we add them? I'm pretty sure we add them. You've made me go, oh no, do we add them? We should add them, shouldn't we? Because if P to Q goes 2, and then it's 4 more from Q to R in the X direction, in total, you've got to go 6. So that would be PQ plus PR. Okay? Which is 2 plus 4. QR, thank you. Right, QR minus 3 plus 5 and 1 plus 6, which is 6, 2, 7. Okay, so the last thing I subtracted from this one I've added. Okay, so let's work out why that's the case. So if I think of OA, if I've got my three-dimensional X, Y, Z, X, Y, Z, okay, if I put a point on here, it doesn't matter where I put the point, it's floating in space and perspective, it's not going to be in the right place anyway. But if I put my point here, that's A, and my point here, that's B, OA is describing this vector to B, and OA is describing the vector to A, OB is describing the vector to B. When I try and find AB, I've got this vector here. So when I'm going A to B, I'm actually doing the opposite direction of A when I'm combining them. Do you remember how the arrows had directionality to it? Yeah. So if I was to go back to my two-dimensional one, if I swapped B to say it's that direction, if I go the opposite direction along a route, I need to now say minus. Okay? So OA is describing the origin to A, and OB is describing the origin to B. But if I'm going AB, it means I'm starting at A. I'm going the opposite direction to OA. So I'm going negative OA, and then I'm going the positive direction towards B. So it's positive OB, so OB minus OA. Okay? Whereas with PQ, QR to get to PR, I've got P, I've got Q, I've got Q, I've got R. I know PQ is that direction, hence the arrow. QR is also is that direction, so it's not the opposite direction. So when I want PR, I'm not going along the opposite directions in any way, shape or form. Okay? So there is an element of thinking about, well, what would these lines actually mean? Okay? If I had said RQ was this, you'd have to do a subtraction, because it would be the opposite direction to which you want to travel along that line. Okay? So there is an element of that sort of thinking, but it doesn't really come up too much with a subtractive nature or positive nature. All right, so that's kind of how you put vectors together. We're all good with that? Yeah, it's kind of what you've been doing. It's just adding or subtracting depending on the situation. If I said I've got the vector, which is PQ, which is, well, let's use a different letter. I've used P and Q enough. FG. Okay, F to G is 4, 6, 5. Okay, and let's say I've got another vector, which is H to I, which is 12, 18, 15. What can you tell me about those two vectors?
So 3FG is equal to
Okay, so what was that?
3FG is equal to HI.
So if I had 3 lots of FG, it would be equal to HI. So what does that tell you about anything? Can anyone tell me anything about that?
All in the same direction.
They're in the same direction, which means parallel. Okay? So, if two vectors are scalars of each other, you're good with the word scalars? Yeah, so one is a multiple of the other. Okay. If two vectors are scalars of each other, they are parallel. Will they ever meet? No, because they're parallel. That's the pure definition of parallel. Okay? Yeah, they'll never meet. So you'll never be able to find out where these two lines cross each other, for instance. Okay? And I'm pretty sure we do, in fact, we do look at vectors and where they would meet, / if they'll ever meet. Because vectors, especially in 3 dimensions, have a lot more options of yes or no meeting. Okay? In 2 dimensions, you've either got parallel or they will meet. In 3 dimensions, you've got parallel, or they're going in completely opposite directions, or they will meet. There's lots of different options with 3 dimensions, which is fun. It's fun. And that's like the last thing we look at in this topic. Okay, so no scalars. Scalars are fine. What else could you tell me about FG and HI? They're parallel. Is there another relationship to do with just... Yeah. Right, so that's... Yeah. Well, it's not... I don't know if it's really considered a gradient when it's in 3 dimensions, but same angle, same... It would have the same... I don't know how you describe it, to be honest.
Wait, is it only similarities or?
Yeah, what's the difference?
They start at different points.
They would start at different points, unless F... Actually, technically, you could say that F and H could actually be the same starting point, because it's undefined. If I gave them the same starting point, they'd have the same starting point. It's just that those 2 points would appear on the exact same location. Most likely, they would have different starting points. Anything about the length?
One's bigger. One is 3 times longer.
One is 3 times longer. Okay, HI is 3 times longer than FG. Okay, so in terms of magnitude, it's 3 times the size as well as parallel. Okay, cool. That's just a basic thing. Scalars, parallel, easy. Right, magnitude. Let's just give out the title scalars. Magnitude. Pop, pop. Yeah, there we go. 1 person. Yeah. Yeah, it's a TV show. Right, magnitude. Okay. How do you find the magnitudinal value of a vector? If I have AB is 2 minus 3, 5. How big is that? In terms of a length, do some Pythag. Yeah. Okay. I just didn't hear you, to be honest. Right. So, let's give a bad sketch again. This is A. This is B. Right. You can break down, guys, you can break down your vector into its x, y, and z directions. So this would mean I'm going 2 in the x, I'm going down 3, and then I'm going depth 5, which would not look like it's over there, but let's pretend it is. In fact, that's a better way of doing it, isn't it? Right. Okay. B. Okay. So I've gone 2 this direction, 3 that direction, 5 that direction. Yeah? So I've gone 2 in my x direction, I've gone 3 down in my y direction, and I've gone positive 5 in my z direction. Okay? What kind of shape does it kind of fit into? Not it's a 3-dimensional shape, guys.
Triangle. Wait.
Cuboid. We're in a cuboid. Alright. So, all vectors can basically be fitted into a cuboid. Okay? With an x, a y, and a z. Yes? In the same directions? Well, in like 90-degree directions?
Going from one side of the cuboid to the other.
Yeah. You go from the top corner of a cuboid to the bottom corner of a cuboid, basically. Well, top left to bottom right, in this case. So, you could break it down into Pythagoras, where you first work out the x, y value here, because you know the angle here would also be 90 degrees. Okay, so there's a 90-degree angle there to create this triangle to get the hypotenuse here. Use that hypotenuse to find that length. To use that hypotenuse there with that length there to find the overall length. Okay, so what you'd end up doing is 2 squared plus 3 squared, square rooted to find this hypotenuse here. Whatever it is, 4 plus 9 is 13, so root 13. Okay, you'd then do root 13 squared plus 5 squared, square rooted. Okay, what is root 13 squared? 13. So you end up with 13 plus 5 squared underneath here, 25, 38, root 38. Okay. Did I need to do 2 steps to do this?
No.
No.
2 squared plus 3 squared.
What was that? 2 squared plus 3 squared plus 5 squared.
Square root. Okay.
When dealing with 3-dimensional Pythagoras, it's just for 3 sides squared to go opposite corners in a cuboid. Added together, square rooted. Because when you square root your hypotenuse, you immediately square it back out again. So this bit here is that bit there. It's for 2 squared plus for 3 squared. Okay? So, one thing that I should have actually done, though, is rather than saying positive 3, because I visualised this properly, in my visualisation I've gone, oh, that means 3 down. Okay? But when you're dealing with the actual values that they've given you, what you should be saying is 2 squared plus minus 3 squared plus 5 squared. Which is ABC. I think previously I wrote X, Y, Z here, didn't I? No, I didn't write that. Oh, I did. A, B, C.
Oh. Wow.
Yeah, well, I changed that vector thing to ABC. The reason why it's ABC, guys, is because we don't tend to write the vector as X, Y, Z. There's another way of writing a vector, which I'm going to show you in a second. Okay? But that's how you find magnitude. Everyone okay with that? Cool. Right. The other way of writing a vector is in something called IJK notation. IJK notation. Okay? Which is AI. Alright, guys, 1 second. So, this is the other way of writing a vector. AI plus BJ plus CK. And we can definitely tell the maturity level of some of the boys in this classroom. Okay? Also, one girl giggling as well. Right. So, with vectors, we use I, J, and K to describe the direction. Okay, I is the direction in X, J is the direction in Y, K is the direction in the Z axis. Okay, we don't tend to use X, Y, Z. X, Y, Z refers to a point. I, J, K refers to a direction. Yeah. So you won't ever see the vector. You will potentially see X's. Some like, don't matter. Just know that we can write a vector like that. Moving on. Which one? IJK. I is just the direction in X, J is the direction in Y, K is the direction in Z.
Why did you write it with I?
Oh, okay. So, guys. AI, you mean? Yeah. A, B, and C represent the value, the coefficient.
Oh,
So this one here, AB, could be written as 4I minus 8J plus 3K. That's the same vector. Okay, so you either write a vector in the vertical form, or you write the vector in the IJK form. Okay? Is that all right? Cool. Yeah, so you'll see both. It can either will appear in the test, but I'll either write it in IJK or I'll write it in the bracket form. And they may ask it for in a certain form. They may say in terms of IJK, or they may not state which form they want it in. It just really depends on the question. Right, so moving on from this for magnitude. So that would be root 38, whatever it is, okay? Which you can do on your calculator for an actual value of like 6.15. I don't know. Don't know what that is. All right, last thing, guys, is a unit vector. Okay, so if I've got AB is 2, 3, 1. I can't be bothered getting new numbers. Right. If I've got the vector AB, which is 2, 3, 1, the unit vector that describes a translation, or that describes the direction or whatever, what we're going to say, the unit vector, I don't know, that describes the direction. Okay, the unit vector that would describe that direction would be, 1 second, just waiting for the guys about 2, 3, 1 times by 1 over the magnitude of AB. Okay, oh, sorry, I should have shown you over here that this stuff here is called magnitude. Do you see those two straight lines? That's modulus. Have you heard modulus before? Okay, modulus means to take the positive values of, but in vectors, that is the magnitude. I can't spell magnitude. Okay, so it's 1 over the magnitude times the vector. So I could also write that as 1 over AB times AB. Okay, so for AB, which is 2, 3, 1, you'd do your 2 squared plus 3 squared plus 1 squared to get the mag AB, square root it, 4, 13, 14, so we get root 14, okay? So the unit vector would be 1 over root 14 times 2, 3, 1, okay? What that does is it calculates the same direction as 2, 3, 1. So we're going in the exact same direction as 2, 3, 1. We're parallel to it. But the length of that vector is 1. Okay, that's what a unit vector is. It's the length 1 in the same direction. So the length of that vector is 1. That's why it's called a unit vector. Okay? And you might see that in some other instances, like I can't remember what it's for, but like there's a unit method for something. I think it's like ratio. You can use something called the unit method, where you create the ratio 1 to something.
Oh, like in chemistry.
I mean, it scales up quite nicely. Yeah, unit ratios, I think they are. I don't know exactly off memory, but basically, because the magnitude of 2, 3, 1 is root 14, when you multiply it by 1 over root 14, what does that become? Root 14 times 1 over root 14 is 1. 1. So it's mag 1. Okay? So that's what we're doing with a unit vector. Once you get a unit vector, you can then scale that up. So if I wanted a vector which is 6 times the length of AB, but in the same direction as AB, I would just times that by 6. So it'd be 6 over root 14 times ABC values. Okay, I'll say it again. So if I want a vector which is parallel to AB, but 6 times the length, okay? What you do is you take the unit vector, which is 1 over mag AB, times the direction, AB, and then you multiply by 6. So you take the unit vector, times it by 6. So in our case, it would be 6 over root 14 times 2, 3, 1.
Is it? Oh, sorry.
What? Where did I lose people there?
Wait, so like it's for each direction, like how much it has to move in each direction. So like
Yeah.
if you like follow through, it would say how much you have to travel in each direction.
Yeah, so if I was to actually finish off this vector, which I should do, you'd end up with 12 over root 14, 18 over root 14, and 6 over root 14 would be that vector, which is 6 times... not 6 times length. Sorry, that's stupid. I'll just times every value by 6 for that, sorry. But is 6 long, is what I'm meaning. 6 long. So same direction, but only 6 units long. Sorry. Yeah, if you wanted to do 6 times length, you just times AB by 6. All the values by 6. Sorry, but that's probably where all that blank looks were coming from. What I meant was 6 times the 6 units long. Okay. Sometimes with the unit vector, you'll see it just written as one thing. And in reality, you should actually simplify it down to 2 root 14, 3 over root 14, 1 over root 14, if you're writing it like that. Or you may end up writing it as the IJK notation, which is 2 over root 14 I plus 3 over root 14 J plus 1 over root 14 K. Okay, so depending on how they want you to leave it that way. But technically, that quite often is acceptable for the unit vector, just saying 1 over root 14 times the vector direction. But generally as well, they mix that up with finding AB. So they might give you OA and OB, and then they say find the unit vector AB. So first you have to find the vector AB, and then you find the magnitude, and then you times by the 1 over magnitude. And it's a 4 or 5 mark question. Okay. Cool. So that's a lot. Welcome to vectors. The questions in the book are kind of jank. But you can have a look at him. I would suggest you kind of skip to question 5, which is basically the last 3 questions.